Hi, I'm Jamie. This is Dead Dodge Garage, and this is my budget 318 build. This is my 1979 Dodge W200 Power Wagon project truck. It currently has no engine under the hood and an automatic under the floor that's probably not going to be there much longer. Next to it, we find the remains of a 1978 Dodge W100. This truck was a complete truck at one time. There are a bunch of various parts from it left sitting around here in various places. I've sold or used a whole lot of parts off of this thing, and as you can see at this point, I'm left with a frame, a gearbox, a front axle, and a manual transmission. The 79 truck belonged to my friend Jordan for a time. We've seen it in previous videos, one where we rescued it from the side of the highway in Idaho, where it was very much blown up, and another video where the 360 got yanked out and torn down for science. Somehow, the 360 that had been in that 79 Power Wagon, which had been rebuilt with some pretty decent components actually, did this to a couple pistons, ate all of the oil, and then exploded in glorious fashion. I've got multiple things to remember this poor engine by in my trophy case. Here's the block from that totally destroyed engine. It was full of metal shavings, and as bad as the mains looked, well, some of the journals didn't look the best. I'm sure this could be saved with some machine shop work, and it may well be someday. I really don't want to invest thousands of dollars in a fresh engine for this 79 Power Wagon. I like it quite a bit, but it's just not worth that. So I was looking for a candidate for a budget rebuild, and that's where this thing comes in. This 318 engine, like so many others before it, had succumbed to a failure of the nylon-coated cam gear. The timing had started jumping around like crazy, and when I opened it up to fix that, I found a bunch of chunks of cam bearing in the oil pan. So that was the end of that. Aside from the disintegrated cam bearings, one scuffed up main bearing, and this rod, everything else in this engine looked really good, prime for reuse in a budget build. Okay, it's been a while since I touched this and I forgot some details. You're gonna have a lot of that around here. Anyway, actually, like most of the main bearings were a little scored up, and all of the journals have little grooves in them as well. In previous Engine Wednesday videos, I tore this thing down, investigated it to find the previous issues, honed the crap out of it in preparation for this rebuild, and then in the last installment, I replaced the cam bearings here at home. I don't know about at your house, but around here, when I'm doing a build and I run into anything more major than a mild inconvenience, I have a tendency of pushing projects into the back line and leaving them there for months. Such was the case with this engine and the cam bearing replacement. In that cam bearing video, I knocked the new bearings into the center of their journals in this block. Then I realized that the oil holes coming up from the mains were drilled off center, and the three center bearings had the holes offset somewhat from those openings, restricting the oil flow to these bearing surfaces. I didn't notice when I was taking these old bearings out, but you can actually see a witness mark right here showing that this opening was offset from the hole in the bearing ever so slightly from the factory. That offset was particularly bad on the number 2 cam bearing, but numbers 3 and 4 were also not right. I spent quite a bit of time ignoring this issue and then a little bit of time thinking about how I was going to solve it. I had some different ideas, one involving a long drill bit, but ultimately I decided to just open the holes up with a small round file, starting from above from both directions, moving the hole towards center of the oiling hole, and then bringing the file in from underneath and finishing the holes that way. I started doing this by hand, which gave me a blister on my thumb, so then I incorporated the vice grips. As you can see, this action results in a slightly irregularly shaped oil hole, but it's now opened into the feed enough that we should have sufficient lubrication here. The filing action left some small burrs around the openings. I cleaned those up with this 800 grit sandpaper. I would have used 400 grit, but I didn't have any. It's actually not at all uncommon to have to carefully sand some nicks out of your cam bearings after installing them. This is something my machine shop often has to do. They utilize a checking cam to make sure the bearing surfaces are good and the bearings are in there straight. I'm going to test my bearing fitment with the actual cam we'll be using. This is the used comp out of the blown up 360. It seems to have survived that experience okay, except that there are bits of aluminum bearing material jammed into a bunch of the lobe surfaces. I'm cleaning that up with a brass bristle brush. This is usually what I use to clean rust and such off of cam lobes. We've got a bit of that back here too. I'll probably lubricate the bearing surfaces, install this thing, and as long as the fit is good, I'll just leave it there. I'll brush cam lube onto these lobe faces later on. Before installing this camshaft, I suppose I should mention I already got all the metal shavings out of the oil feed holes, wiped the bearings down, etc. This block is pretty much ready to go. It's not like it's clinically clean or anything, but it's good enough for me. In anticipation of reusing this camshaft, I saved the lifters that were on it in order in the positions they came out of, and they'll be going right back to those positions in our new block. These need a cleaning too, like a pretty serious one actually. Oh yeah. She's minty. Note, I did have to knock the rear cam plug out to do the bearings. I've since reinstalled that, sealing it with some of that aviation liquid. The other important thing that needed to happen before this build could continue, hardware cleanup. Now, Alan already put a bunch of time into getting things like the timing cover, the oil pan, the intake, the damper, all that stuff looking really good. The heads still need a wash, but don't worry about that. But the bottom end hardware, the head bolts, all of that stuff needed a good cleaning. Well, as you can see, that's now done, and it was really easy. As I mentioned in my recent 361 teardown video, I now own one of these Vevor ultrasonic cleaner thingies. This is the 30-liter size. It's full of 3 gallons of mean green and some water to dilute it. I've had this thing running in the background like every time I'm in the shop for the last week since setting it up. It's amazing. It might be my favorite thing of ever. And while I was working on that 361, I was also cleaning the stuff for this 318 in the background. It's really amazing on factory bolts because these are coated. It doesn't eat the coating, it just cleans all the gunk off of there, so they come out looking really good. Some of them will look a little rusty, like these, because they live outside of the engine and they're exposed to the elements. But the stuff that's inside in oil, it comes out looking absolutely perfect. Now your machine pieces, your main caps, your plates, things of that nature, they do not have any coating on them. And so when you take them out of the ultrasonic, you need to dry them off really quick and then coat them in oil, which I've done to prevent flash rusting. I've got a set of push rods here that are clean and ready to go. These are actually out of the blown up 360. I'm using a bunch of hardware out of the original 360. The cam retainer, the eccentric plate, the drip tray thingy, and all of the head bolts. I don't actually know why. They were just closer at hand when I was cleaning stuff, I guess. Now again, the crankshaft was one of the bigger issues with this 318 because all of the main journals and at least one of the rod journals had appreciable grooves in them. So I needed a different crank. I grabbed this one out of my stash. This is a stock size 273 forging. These forged steel cranks are the ultimate in factory small block bottom end strength. It's probably overkill for this build. That's going to be a recurring theme, but it's what I've got, and so I'm going to slap it in there. The balance is like slightly off, judging by the weights between the rod and piston assemblies for the 273 compared to the 318. 273s used a heavy wrist pin to get them close to the weight of a 318, but they're still not exact. I think it's going to be close enough for what I'm doing. The other issue, though, very small bits of rust staining. Notice here on the 7 and 8 journals, and then there on the number 5 main, there was just a little bit of rust stuff that I had to clean off of this. I've now done that, and I'm happy with it. With that, it's time to start assembling this engine. We'll start with the main bearings. These are some new old stock Michigan branded bearings. They have the FM Federal Mogul marking on the back of them, but they're in boxes that say Michigan. These are in a standard size to match this crank. I have a bunch of these from the Dave Wren estate. It's not often that I need basic factory size main bearings, so I'm glad to be using some finally. These are a factory style half groove bearing. Note, only the block half is going to have that oil groove. The cap half is going to be smooth just like this. I will be reusing all of the stock rod bearings except for this one. To replace that one, I got one male, or however you pronounce that, CB481P standard size rod bearing set. At least one commenter on a previous video on this build said, "Why wouldn't you just replace all the rod bearings?" Which part of budget build did you not understand? Look at these things. I need to wipe some dust and gunk out of there and give them a final cleaning, but they look really good. Yes, there are minor little score marks on the coating of the bearing, but nothing you can actually feel. That doesn't matter at all. There is no reason to throw these perfectly good rod bearings away. Breaking the seal here on a brand new Felpro full engine gasket kit to get the rear main seal. This is the part number I've been buying from O'Reilly lately. It's 260-1152. It only has the 70-ish onward 318 oil pan end rails. It doesn't have the early style with the little tits on them. And it doesn't have the smaller 361 either. In case you didn't know that, the sealing areas between a 318 and a 360 pan, despite being very similar, are not the same. It does have both intake gaskets, the metal 318 gasket and the composite 360 large bore gasket, so that's nice. The head gaskets are not ideal for a 273 or a 318. Unfortunately, we're going to have to use them here anyway. I don't have anything else. These are the typical Felpro rebuilder gaskets. They're a composite gasket that's something like 40 thou thick compressed, and they have the big compression ring here that accounts for the largest oversized 340. I have to give a quick shout out to a gentleman named Tony who tried to find me some of the correct head gaskets for these 318 builds. He was told by a supplier near him, north of the border in Canada, that he had those gaskets. What he shipped out are the 360 type. so they really don't do us much more good than the Felpro gasket here. I've only recently learned that Mr. Gasket has a steel shim gasket available that compresses to about 20 thou. That would be a better option. It still has the big combustion ring, and it also costs like $90 for a pair of those. This does not deserve that. It does deserve to have less hair in it though. Anyway, there's the upper half of the rear main seal installed. Notice I install these with the ends flush to the block. I was told by a commenter recently that they offset theirs by cutting these little ends off, putting them in the cap separately, and then spinning the center section. I do not recommend that. As I understand, these are supposed to be installed flat like this. These ends are supposed to compress against each other. They're not going to do that right if you cock them off at an angle. So here's the lower half installed in the number 5 main cap as it comes, as well as the number 5 lower bearing. Note that one is fully grooved. That one always is. Here's a reminder once again to clean your bearing shells before you install them. Just because they're new and in a box does not mean they're clean and ready to go. Here's what came off of the block half of the number 5 bearing. Ugh. I've always used a finger, ideally slightly cleaner than this one, to swipe oil onto the fresh bearing surfaces before installing the crankshaft. Some commenter on a previous engine build video said that the acid from your skin can damage the surfaces of these bearings. I can't be bothered to worry about that. And speaking of things I can't be bothered to worry about, if I was a real engine builder, or this was a real engine build, I should be measuring oil clearances right now. But I'm not going to do that. I'm just going to slap this thing in here and see how it spins. Spinning it and feeling for things is what I've always done with these builds. And I just caught something doing that a clearance test wouldn't have. Note this little scratch that's now found on our number 5 main bearing shell up in the block. I don't know if you'll be able to see this because I've already kind of cleaned it up with some more of that 800 grit sandpaper, but it turns out there was a ding in this crank just like the rod journals of that 383 crank I showed a couple weeks ago. I don't actually remember where this crank came from, but I'll tell you this, it really should have been polished. Anyway, moving on. It's the next day because I had to go build a recording studio in a garage from scratch for some reason. Before moving on with this build, I want to discuss a couple things real quick. First, the little groove that was left from that nick, which I've since sanded down, you may notice is only obvious here at the sides and not in the center so much. This is because, just like the halves of the rear seal, the halves of the bearing actually squish together and they don't take their final shape, expanded out into an actual circle, until they are torqued down. That means when you first drop your crankshaft in here before you torque the caps down, you don't actually have your proper oil clearance out here at the sides of the shells. Typically this would be fine and you could still spin the crankshaft without any worry of damage, but obviously in the case of our nick here, that clearance was well under what it should be. So it did unfortunately scrape the bearing a little bit, and I'm not excited about that, but it's not going to be a problem ultimately. Those spots will hold a little bit of extra oil, but we'll be just fine. The other thing I wanted to discuss is more of a broad idea because it's occurred to me as I'm screwing this cheapo, mostly factory 318 back together, that oftentimes in these videos I will mention the thing you should do and then almost go out of my way to not do that thing. It shouldn't be breaking news to anyone that watches these videos that I am not a world-class engine builder. I am not an expert on the subject. I do things in a certain way, a way that has worked well for me over the years. The vast majority of the drag strip runs I've completed in my life were made using engines I built with the same methodology. I've put engines together with used cams and lifters and random old factory parts. I've thrown darts on compression ratios. I've made educated guesses. I've slammed many small and big blocks together with less than ideal machining and what have you. And I've had pretty good results. Everything I do here is based on my years of experience and my standards, but they may be very different from yours. And I guarantee you they're very, very different from a real engine builder, a professional engine builder. You know, the Just Mopar Joes of the world. If you can take one thing away from my build videos, I hope it's this. Pay close attention to details, scrutinize everything, especially new stuff, and make sure everything you're screwing together in your engine is clean. Also, if it's an important lubricated surface, put some oil on it. Oh, and torque all the important fasteners to spec in the correct order. That's a good one. Every engine is a little bit different. Every situation demands a different level of quality, a different part selection, a different amount of attention to certain little details. I cannot demonstrate to you the correct way to do so many parts of these projects. Sometimes I don't even know what that is, and other times I'm just bad at it. What I can demonstrate to you is the way that I do things and the results. and hope that that serves you well in some capacity. Anyway, it's an hour later because I'm just one man and I have to make videos, but also edit them, answer comments, and respond to emails. And I've got the main bolts torqued down to their first stage, 35-pound feeties. You'll notice I did put a flathead screwdriver in here to force the crankshaft forward and align the halves of our thrust bearing. With this first torquing stage done, I should now be able to check our thrust, which looks about right to me. I could put a mag-pace dial on this, but I'm not going to. Of course, verifying proper crankshaft thrust or end play on this engine is like polishing the brass on the Titanic, because it'll live in front of a truck 4-speed and the action of actuating the big 11-inch clutch will probably wipe out the thrust surface before we know it. This thing will have a 16th inch of end play, but it's a nice idea. Anyway, I've now got the mains torqued down to their final number of 85 pound-feet. I've marked the bolts with a paint dot, as I often do, and we're good to go here. As I've mentioned, I own an ultrasonic cleaner now, and I could certainly dunk these pistons in there to get them looking spiffy. However, I kinda already hand cleaned them, mostly. I have done some light file work on this one. See, there's a ding here, probably because I dropped it when I pulled it out of the engine. Also, those valve contact marks that every piston has, I'm filing them down smooth as well. And now for the million-dollar question. Do I flip the pistons or do I not flip the pistons? Much has been said about reversing the piston pin offset with factory-type offset pin pistons by swapping them from bank to bank. Most of that has been said by Uncle Tony, although there have been many other discussions about this in recent months. Everyone seems to have a slightly different explanation of how and why this would work. What I do know is that this modification is explained and advised in the direct connection manual. Tony has explained this as changing the angle of the rod, increasing the amount of power that's able to be utilized by the moving piston. Others say it reduces the amount of friction between the piston skirt and the cylinder wall. I've heard it said that flipping the offset changes the stroke of the engine, which is impossible. Recently, in a comment on one of my videos, I was told something I'd never heard before, that reversing the pin offset will change the ultimate height of the piston. You can improve the compression ratio of your engine, therefore, by flipping this around the other way. This does not make sense to me either. This engine, with its factory pistons well below the deck surfaces, is certainly compression ratio challenged. I'm changing to a set of closed chamber heads for this thing, but I would make any other changes, if they were quick, easy, and cheap, that would bring up the compression ratio. Then I realized I can actually measure this. So what I'm going to do is put the number 1 piston in here, measure the deck clearance, and then swap the number 2 piston into the same hole and see if there's a measurable change. There's no guarantee 2 factory pistons have exactly the same compression height, and there's no guarantee that the machined openings in the rods between the big and small ends are exactly the same. But I think it's worth checking anyway. The other thing we could do is see if the top dead center point changes between these two. As that offset is moved, does the crank need to move a few degrees to compensate for that? I'm not sure. Here's number 1 dropped in the hole. To make this fair, we do need to torque the rod down, so I've done that. That is a nice moving piston. Of course, it should be with a worn out rod bearing and tired old rods. Anyway, we'll bring this up to TDC, which I will verify with the mic in a second here, and then we'll take our deck clearance measurement. I found TDC as accurately as I could with this mag-based setup. I found the spot where the indicator stopped moving, and then I carefully centered in on that to find my best guess at perfect piston dwell. I've now marked this with a black marker. That's as straight a mark as I could manage. And we'll see with number 2 in there if that moves at all. I did show this process for checking deck clearance on my recent 361 teardown video, so I could do a rudimentary compression calculation. Note this is zeroed as close as I can get it. I'm going to lift this and carefully twist this over to the piston top with 2 hands. You don't want to go right on the edge of the piston because it has that sort of curved shape to it. You need to go out here somewhere. Obviously, I did try to ensure that this was straight up and down this way and that way, so this should be a relatively accurate measurement. And of course, this is going backward from 0. There's 0, 10, 20, 30, 40, 50, 60, 70, 8-ish? That's almost exactly what I measured on that 361. Incidentally, it's significantly less than I measured on my 225 performance build here. This came in at like 104 thousandths in the hole. Measurements that are not repeatable are not good measurements, so I repeated my measurement a couple times, and I came up with 76 thou. I'll never be able to get any more accurate than that. Number 2 piston is in. First thing first, I rechecked our TDC mark. It sure looks exactly the same to me. Now again, this is not the most precise thing in the world. I'm not the best at using one of these things, but I did repeat this measurement several times and it came up the same each time. 83 thousandths. So this one is farther down in the hole. And if you really sit down to think about it, this makes perfect sense because the offset has moved the pin downhill that way, therefore pulling the piston down ever so slightly. Again, by doing this, I could be measuring a difference in the compression height between these two pistons. I don't seem to be though. Of course, my measuring equipment is notoriously terrible, but near as I could figure, these are exactly the same. The other possibility would be a difference in rod length. This is not an easy measurement to make with these things put together and the measuring equipment I have on hand, but I did try, and as near as I could tell, they're either exactly the same or that one might be like a thousandth longer, but that's nothing. So as near as I can tell with what I've measured here, not only does flipping the pistons not increase the compression, it actually lowers it ever so slightly. Maybe I don't understand how this works, but I don't see how moving the pin there improves the rod angle either. Because with this, the number 1 piston, the one I took out of the number 1 hole, the notch facing forward, the pin is offset this way, meaning the rod will be like that, favoring the direction of crankshaft rotation. While this one would actually be more vertical for longer. The crankshaft, of course, rotates clockwise when viewed from the front, and that means that as the pin is rolling over, this rod will be at more of this angle, while this one will be that way. I did have the random thought to make sure that offset was the same as another offset piston. This is one out of my slant 6 build. It is indeed the same with the notch forward. The pin is offset that way. If I'm not understanding this correctly, please tell me in the comments, but I don't think I'm wrong. With this crank, for example, coming off of TDC at this angle, the rod would look like that. But if we put the piston in backwards, the rod would be more vertical. And it's supposed to be that rod angle, especially in a long rod engine like our 225 slant 6, that prevents this piston from doing work before the crankshaft has moved over a certain amount. So I should think having it that way improves things. What I do know is the compression height measurement I took today is enough to convince me putting them in the way they came out is the move, at least on this engine. Now, if you do want to reverse the pin offset for science or whatever, I do have to remind you, when you flip these pistons side for side, you have to rotate them. The number 1 with the notch facing this way puts the notch in the rod bearing there toward the odd side oil pan rail. If we were to put the number 2 piston in there, the notch needs to face backwards and the notches for the bearing would again face to the odd side oil pan rail. If you flip them side for side, but you don't flip them around like the last assembler of my 383 engine did, you end up with the notches in the bearing facing the wrong way, which points the cheek of the rod, the raised side of it, the wrong way. In addition to that, because the notch is still facing forward, you haven't changed the offset at all. I feel like it's really important for everyone to understand that these pistons are the same left and right. Obviously, that would be different if you had asymmetrical valve reliefs. And because this is a press pin, you don't want to flip them around in the same holes. You'd have to take them off the rod to do that. For science, we're back over here at the Summit Racing compression ratio calculator. I do want to note this thing isn't necessarily the most precise tool in the universe. One thing that's absent here is the diameter of the hole in your head gasket, which can affect things more than you might think. Especially on our 318, we're going to have to use a 360 gasket for this because it's all I have access to, and so we will lose a little bit there. Anyway, I've punched in our numbers: factory bore size of 391, stroke of 331. Our cylinder head volume is a guess. I've put it at 62. That may be a little optimistic. I am not going to take the time to CC our 714 heads from the 90s. I can't be bothered, and I also don't have the proper equipment here to do it. If you're building some kind of fire-breathing monster with aftermarket components and extensive machine work, you need to check all these numbers and verify that your compression ratio is survivable. I'm building a cheap factory-based piece of garbage. Of course, we've got no dome. This is a factory flat top piston. It does have a bit of a rolled edge, and I probably could account for that, but I'm not going to. I put in the deck clearance of 76. Oh, I'm grubby. And then the thickness of our Felpro gasket, which is 0.039-ish compressed. That yields 8.7 to 1. Cheapo, unleaded 87 octane in a truck engine? I'm good with 8.7 to 1. Swapping the 76 thou number out for 83, what I measured when I swapped the number 2 piston into the number 1 hole, gives us 8.58 to 1, which is less. It's not a huge change, but I don't think it's a change I'm going to make. Anyway, now it's quite a bit later. We might have all actually learned something for once, and I'm moving on. For science, I decided to measure the deck clearance for piston number 3. Probably shouldn't have done that because for some reason it's at about 82 thousandths or a hair over. I didn't want to know that. I'm going to continue pretending I didn't. Number 5 is the one with the damaged rod bearing. I forgot it also has stuck rings. So I need to get this fixed, probably with a small torch and some mild beating. Actually, the top one didn't even come to that. It was only half stuck. I sprayed it out with some brake clean and then soaked it in some PB and carefully worked on the side that was not stuck, springing it in and out, and it gradually loosened it all the way around here. You can see a good bit of rust. Ha-ha! Second one's moving too, simply by spraying it with some PB, then spraying it with some brake clean, scrubbing at it with a wire brush, and then gently tapping it with the wood handle of that brush. I've got it about half free now, and I guarantee you it'll be fully moving in a second here. It's a while later, and I have these rings cleaned up to my satisfaction for piston number 5. They're still not the prettiest things in the world. There is some light staining and pitting in a few places, particularly on the second ring, but I still feel okay using these. The reason for that is, especially this top ring, shows zero evidence of terrible blow-by. No big scorched sections where combustion gases were getting past. They look uniform and really good. 80. So I guess number 1's just our good one. Last week, I did a video on this 361 cubic inch big block. I'm doing a very similar budget overhaul on this engine to install it in my 1957 Dodge Coronet. In the video for this engine, I went through the same exact process of measuring the piston height and calculating the compression ratio. In the comments on that one, multiple people asked, why don't you just have that block decked to raise the compression ratio? Well, it's an easy answer. I don't want to involve a machine shop. That's the entire point of a budget build like this, to get away with what you have. To have a block like this decked, it needs to be fully torn down and dragged into the machine shop. There, they will give the thing a complete cleaning before machining it and then giving it a complete cleaning again. Our local machine shop, Johnson Machine, which isn't all that local, it's actually like an hour from my house, uses a process they call custom clean because they don't have an acid hot tank anymore. Those things are kind of going the way of the dodo bird for good reason. Multiple people have commented on my videos building engines with blocks that they've done and have said, wow, that looks amazing. It looks almost brand new. How do they do that? Well, it's this custom cleaning process. I've never seen it done. I don't know the exact procedure, but my understanding is that they bake these things, wash them, and then they go for a ride in a tank full of shot. I think it's some kind of vibrating process. The steel shot knocks little chunks off, and then the block gets washed again after that. During this process, the shot abrades the bore surfaces, as well as every other machine surface. So, after the custom cleaning, pretty much everything has to be redone. For that reason, we do not do this cleaning process to a block that's going to be rebuilt with the same bore size it already has. During this cleaning process, the cam bearings have to be replaced too. So there goes another $80 for every build you do that to. Also core plugs, don't forget core plugs. Machining the deck surfaces on a block does not just cost the amount of that one operation. It costs the amount of that operation, a cleaning, a set of cam bearings, a set of core plugs, and a set of new pistons. Because again, after this custom cleaning process, the block has to be bored. Of course, if you're doing all of that, you can just go for a taller, higher compression piston instead of decking the surfaces, unless you're building, say, a slant 6 or a 361, and performance pistons don't exist. Anyway, hopefully that heads off some questions on this build. It's the same answer as so many other things, a cost-benefit analysis. And in this case, it's just not worth all of that cost to raise the compression. Astute members of the viewership may be wondering about this shiny ring on the outside of the number 5 piston. This is from cleaning it up by hand with a file to knock these dents around these valve contact marks down. I did the same thing on the other pistons. You can kind of see a ring around number 3. There's almost nothing on number 1, partially because I was a little more precise in my work, but also because of differences in the cast shape of all of these pistons. Here's the same process done on the number 7 piston. It is raised a little bit at the outside edge there, but not nearly as much. Over to the passenger side now, and this is interesting. Number 2, which of course I measured in cylinder number 1 bore as 83 thou down in the hole, is back at 75 in its own hole. It's totally possible that these decks are not straight or not level, and that mild differences in where I'm positioning the mic can change the measurements. Obviously the spot I'm hitting on the piston can change it as well. I am trying to be pretty consistent with that though. If I wanted to be really ridiculous, I'd go through and check every one of these pistons for height differences and then flop them around to the different positions to try and make them the most consistent. but I'm certainly not going to do that. Another hour and 1 lunch break later, we've got a full set of rods and pistons installed and torqued. Just for fun and science, hey, what do you know? That thing spins really nice. Don't mind the clunky noise, that's that thing moving around. We're happy. I've got the cam retainer plate and our timing chain set is on. We're gonna check and see what this degree setup looks like. Currently, I've just got it aligned dot to dot. I did turn it slightly, don't worry about that. This is a 3-way adjustable timing set, so I could advance or retard it, I think 4 degrees? So many hairs. Plus or minus 4 degrees at the crankshaft, which of course is 2 degrees at the cam. I haven't decided how I ultimately want it installed just yet, but the first thing to do is verify this circle is in the right place. So this currently lined up in the factory timing position, which is not the square keyway, it's the slightly rounded one. This and this should get us something. I don't actually have the cam card for this thing. Maybe I can find that online. To do these checks, I need a lifter riding on the intake number 1 lobe. So I pulled the lifter tray out. I'm starting to clean these things up, which I think I mentioned I needed to do anyway. I just reached in and squished this one by hand a little bit, and it felt all gravelly. And I saw one little shard of metal sitting on top of this. So yeah, they're gonna get broken down and cleaned. This is your hydraulic lifter on drugs. Here's the main center piston-y section. There's a check valve of some kind in the bottom of it there, and there's a spring that sits under it. It goes like that, and then the cup balances precariously on top. This clip retains that so it can't come out too far. All clean, much less gravelly. Here's the next one. You can see some little bits of debris on there. The first time I pushed on this one, it made horrible gravelly noises too. It has since stopped doing that. Getting the lower piston out can be a little tricky. Jamming my pinky in it seems to work all right though. So I'm gonna degree this cam, except I don't happen to have my degreeing kit. It's sitting at Rocket where I've needed it many times lately. I do happen to have a random loose timing disc that I got from Dale. It's entirely possible he degreed multiple cams in a 340 using this disc. I'm gonna have to borrow a big block bolt, which is shorter, so this will actually be sucked all the way against the crankshaft there. We'll get this lined up, and then we'll take some measurements. I would move this thing over to check the piston movement so I could verify TDC, but I already did that and made a mark. I've covered degreeing camshafts in previous videos, and it's been covered by many other people that know more than me in many other places, so I'm not gonna do that. I got the wheel on, set our tab at 0 degrees when I was 100% sure we were at top dead center. And then I spun it over to find 50 thou tappet lift on the up side of the ramp. And then I continued until I found 50 thou on the back side of the ramp. By adding those two numbers together and dividing by 2, you can find the center line. I did that. It's a little goofy because the 5 there, as you can see, is negative. If you take 215 and add -5, that's the same as subtracting 5. So that would be 210, and then you're dividing by 2 to average between those numbers. You get 105. Then, for fun, to back up this measurement, I watched the dial here as I went up to max lift. I found max lift and then found where it started turning around to go back. I went back and forth and tried to average between those points just kind of by eyeball to find maximum lift. There's a reason you don't do it this way, and that is the dwell time of the lifter is hard to eyeball. But again, I got as close as I could, and we came up with 105 on the degree wheel. So that tells me that the math there was correct. Note, the needle doesn't actually point to 105. You have to count the tens after TDC to get to that number. I don't actually know why degree wheels are set up this way, they just do. The cam card for this used comp camshaft, a 268H, which you can find online, specifies an intake lobe center line of 106 degrees. The fact that I've found this one installed at 105 tells me we're very, very close to what they specify. I did consider advancing the cam even further, but I think I'm gonna leave it right where it is. With the measuring done, I cranked the engine back to TDC1. Now I've explained this in many videos. Countless videos, but I still see people online who do not know or understand this, so I'm going to say it again. TDC1, that is the position in which cylinder 1 fires, is not dot to dot on your timing set. It's both dots up. If you install your timing set with both dots facing each other, that is the dot on this cam gear facing downward, and then you install your distributor with the rotor pointing at cylinder number 1, it will be wrong. It will be what's known as 180 degrees out. This is the 180 degrees we're referring to when we say that, because this camshaft and the distributor rotate half as fast as the crank. So you can line it up on the timing mark, and this will either be right or wrong. The reason we have a gear reduction here is so the camshaft and distributor will spin half as fast as the crankshaft, because this is a 4-stroke engine. Those 4 strokes are up, down, up, down. Those are the piston movements, but the actual strokes in the 4-stroke cycle are, well, these. On one of those ups, we need the exhaust open to exhaust. And on the other one, we need the valves closed so we can compress our air-fuel mixture. For combustion to occur, we need the valves to be closed and ignition about to happen as this piston is coming up on its compression stroke. And the point at which that happens, the point at which these valves close, why is there a bug? The point at which our lobes are away and our lifters are fully off of lift is here. Probably should have started this already, but there's still stuff what needs cleaned. The rockers are one of those stuff. I've got the cleaner thingy preheating now. I'll shuck these things like corn, dump it all in the bucket, and then we'll get that all nice and shiny. I haven't cleaned oil pan bolts for it yet either for some reason, so we'll dump those in there as well. Yeah, maybe the intake stuff. Why not? Oh, right. Horrible noises. I forgot. In the future, I'm going to move this thing away from the area where I actually work. It's slightly obnoxious and in the background of a lot of the remainder of this video. I apologize. I did not forget to torque the bolt that retains the cam gear to the cam. I've got the engine rolled upside down again, hopefully for the last time, to get pump and pickup stuff figured out. It is advisable to always replace your oil pump pickup, and there are good reasons for that. There's the old cam gear. It's pretty much impossible to fully clean one of these pickup screen assembly thingies, but I'm going to try. Also have a question. Why was this thing not tight? Now you might think the ultrasonic cleaner is a good place to clean up one of these oil pickups. Well, this is the one for the 361 and I've run it through many times. I don't know that you'll be able to see this, but there is still gunk built up back there. No, I'm just going to hit this one repeatedly to get all of those chunks of nylon out and then give it the old half a can of brake clean routine. This could take a while. As if we didn't have enough horrible noises in the background. Get out of there. One chunk of nylon stuck in the screen. Got him. I think I've got all the chunks knocked out. It's fairly clean. I feel good about it. Now at this point, the next important question is, what oil pump are we going to hook that pickup to? If you've never seen the show before, you might expect that I ordered a brand new one. No, this is the pump out of the 318, and unfortunately it's had water in it. It's really not that bad. No major scuffing compared to many I've seen. I'm going to try and clean this thing up and see what it actually looks like. Here's some inside baseball in case you've ever wondered how to tell how long filming takes me. The passage of time, the darkening outside sky, well, that's one possibility. But now we have this piece of equipment, which I always set for half an hour, as an extra piece of timekeeping hardware. What you can do is compare the point where I started it to the point in the video where you hear this noise, and you'll know a half hour has passed in real life. A lot of this is looking really good, but I'm going to let it all stew for a second round. Beep. Meanwhile, I'm working on cleaning up the components of this pump. Someone somewhere will have a mild coronary episode when I tell them I've run way worse than this. I just gave this thing a quick cleaning with some 800 grit sandpaper. You can see some scoring there, but it's pretty light and wavy, not like sharp. I think a little bit more polishing and this is going to be fine. There is one weird spot where it looks like a wire from a wire brush went through this pump, or something like that. There's a line on that rotor, and there's a matching line right there. There are also some small little bits of bearing material left behind. I'm going through and getting this stuff out of those surfaces just like I did with the camshaft, and then again giving it a little polish. The housing looks like this. I probably should have put this in the ultrasonic too. Cleaning the housing by hand, which is kind of a gross job. Looking much better than it did. Working on the mounting surface here, as you can see, I went at that with a file. Look at the shiny spots. That's where the file touches. Everything else, not so much. These oil pumps mount from the factory with zero gasket. This mounts straight to the number 5 main bearing saddle cap thingy. And it should have a perfect seal. Kind of hard to do that if it's not flat. Especially hard to do that if it's like dinged on the side. I always check the pumps like this. I never checked the main caps. That would probably be a good idea. Thought I should check this for straightness. Probably a good thing I did because it wasn't. Probably see that raised line there. The pump body itself, much flatter. Obviously, in a perfect world, this thing would be milled laser flat. That's what Chrysler should have done, you know, when they built it. Here we go. Looks good, feels good, and I'm happy. And there we go. The cover plate is back on and torqued. It's filled with oil, tested, working, and it only took that. Was saving $50 or $60 on a pump worth half an hour of my time? I don't know. Something, that. Now I've got the pickup attached to the pump. I even sealed the two with some thread tape. I don't know, I was feeling spicy today. And then I torqued it to the rear main cap. It's not as fun in the dark. I mean, it's still fun, but it's not as fun. Also not as fun at night, this. At least I don't have to walk back. Now I hear what you're saying. You're saying, Jamie, when did you get another lift and put it over there where the Hudson was? Don't worry about it. So proud of myself right now. Of course, now that it's all nice and clean, I noticed some light scoring and a little bit of surface rust on at least this one rocker shaft. This one piece of 800 grit sandpaper I've got on hand is really getting a workout today. I got a thin coating of oil on these real quick, like the other engine internal components. Of course, I can't really do a whole lot about the inside, also known as the part that actually matters. Now, you may have noticed I'm cleaning some factory-type non-adjustable rockers and rocker shafts, even though I indicated in a previous video that I would be using 273-style adjustable rockers on this build. Dude, that's another forged 273 crank I forgot I had. Although I think this one needs the rods resurfaced. Anyway, remember that thing I said about various components being massive overkill? Well, the adjustable rockers are probably one of those. And I really only have one semi-usable set left. I have another set that's like a complete rusted solid chunk of scrap metal, and then some loose arms, and that's about it. So I want to save these for something special. Not anything specific, just something more specialer than this build. This is a truck engine, and it'll probably never see 5,000 RPM. Fast forward to me bouncing off the rev limiter and a tree at the same time. Anyway, the non-adjustables will be fine as long as the base circle on the cam, the height of the lifter, the length of the push rod, and the height of the valves all cooperate in that happy range where these lifters work. In this two-part series where I did a top end and a cam swap in a 1979 Chrysler Cordoba very far from home, we had problems with exactly this same thing. You see, this had a reground camshaft with a smaller base circle than the factory piece, and the lifters ended up farther away from the rocker arms to the point that a few of them had not only no lifter preload, but a gap, which you do not want with a hydraulic lifter setup. After that recent experience, which very nearly turned into a complete nightmare 2,500 miles from home, you can bet your bottom I will be thoroughly checking this thing for proper lifter preload. But that, like reassembling these rockers and countless other operations, is going to be a not today thing. I feel like I say this in every single engine build video I do, but it continues to be true, and I'd hate to break tradition. I really thought I was going to get farther with this. The timing cover is nice and pretty, but I need to knock a new front seal in before I can install that. And we need, or at least really should have, that timing cover installed before we can throw on this nice, shiny, and clean oil pan, which I've only just noticed has been welded in the past for some reason. Truck pans are weird. They have the sump where it actually should be. Also, obviously, I need to adjust the pickup height still. These 714 casting number cylinder heads with the oversized valves are in darn good shape. The valve seals are still squishy rubber, so I'm just going to be throwing them on there, but they do need a cursory cleanup first. And then these, and then those, and then that stuff, and eventually this nice pretty stuff that goes on top. Tune in next time, which will probably be a few weeks from now, because we've got spicy slant 6 stuff to do for a 63 Dark GT, also a 361 to put together for the Coronet, when we'll probably do all those things I just said. Until then, as ever, thanks for watching. And remember, a loose motor is a happy motor. And this one's friggin' delirious. It's not a motor, it's an engine! Shut up, I know. Oh, one more thing. In the last video, I asked what color I should paint this thing. If you know me, you know I like Chrysler red. And most people seemed fine with doing that, so I've decided to paint it blue.